Swayam Prabha. Digital India. Educated India.
Dear viewers, in this session, I will discuss the various data models which can be used to represent data in a GIS environment. Digital geographic data represents real world features and phenomena in a numeric form coded in a specific way to support GIS and mapping applications using computers. To make the geographical data useful, it should be encoded in digital form and organized as a digital geographic database that creates a perception of the real world similar to the perception created by the paper maps. The conventional paper map represents a general purpose snapshot or static view of the real world at a given time, whereas digital geographic database allows a range of operation such as sorting, processing, analyzing, visualizing and spatial data. This allows the data to be dynamic together with the necessary tools for interacting with the data to perform certain specific objectives. Representation of data model. The ways of representing data are known as data models. The data model represents the linkages between the real world domain of geographical world and the computer, or one can say it is GIS representation of the features. The processes of linkages involves, for number 1, identifying the spatial features from the real world that are of interest in the context to an application and choosing how to represent them in a conceptual model. Second, representing the conceptual model by an appropriate data model by choosing between raster or vector approach, and third, selecting an appropriate spatial data structure to store the model within the computer. So, let us look at the modeling approaches that could be adopted. Real world features can be represented as object and phenomena. Objects are discrete and definite, such as buildings, roads, cities, forests, etc., while phenomena are distributed continuously over a large area, such as a topography, population, temperature, rainfall, noise levels, etc. So, let us look at object based models. In object based models, the geographic space is treated to be filled by discrete and identifiable objects. An object which has a spatial feature has identifiable boundaries, relevance to some intended application, and can be described by one or more characteristics known as attributes. The spatial objects may be classified as exact objects or inexact objects or fuzzy entities. So, let us look at what is exact and inexact objects. Spatial objects are said to be exact objects if they represent discrete features such as buildings, roads and land parcels. The spatial objects which have identifiable boundaries, but not well defined, are called inexact objects or fuzzy entities. The characteristics of inexact objects change gradually across the assumed boundaries between neighboring spatial objects. Landform features and natural resources, soil types, forest stands, wildlife habitats are some of the examples of inexact objects. Here, this particular slide shows a graphical representation between the exact and inexact objects. We can see there are three types of information which are in the object space. There is a group of houses, a power line, and beyond the power line there is a forested area. Now, this information can be converted into point information, into a line information or into the area information depending on the type of information which is present. For example, one may like to have exact locations of the houses. So, these would be treated as discrete and identifiable objects, but however, they do not have a spatial extent. These may be represented conveniently as a point. However, the power line being a continuous string of information passing over a given range, the same can be represented as a line, while the forest area may have variety of information. So, it may be prudent to provide the exterior boundary and identify it as a forest area, and this could be represented as a aerial information represented by a polygon. Field based models. The field based models treat geographic space as populated by one or more spatial phenomena of real world features varying continuously over space with no obvious or specific extent. Data for spatial phenomena structured as fields can be acquired directly or indirectly by aerial photographs, remote sensing, map scanning and field measurements made at selected or sampled locations, such as topographic data can be represented by triangulated irregular networks, or in short TIN. The data can also be generated using indirect data acquisition methods by applying mathematical functions such as interpolation, reclassification or resampling to the measurements made at selected or sampled locations. Topographic data such as contours and digital elevation models are examples of data usually obtained by indirect methods of measurements. Spatial phenomena are represented as surfaces which can be thought of being made up of spatial data units in the form of either regular tessellations or irregular tessellations. At the database level, data in object based spatial databases are mostly represented in the form of coordinate lists, that is vector lines, and the spatial database is generally called as the vector data model. A spatial database, when structured on the field based model, the basic spatial units are the different forms of tessellation by which phenomena are depicted. The most commonly used type of tessellation is a finite grid of square and rectangular cells, and thus field based databases are generally known as the raster data model. Having had a look at the representation, now let us look at the spatial data structures. Data structures provide the information that the computer requires to reconstruct the spatial data model in a digital form. There are many different data structures in use in GIS. In general, data structures can be classified accordingly to the type of data they use, that is raster or vector data. Raster data structures. Coding of raster data in the entity model, that is, an image is done by having mirror image of the equivalent rows of numbers in the file structure in the cells in each line of the image where the entity is present. This slide shows a raster data structure wherein the A figure shows a representation of a polygon within a raster data set. This is what we call it as the entity model. Subsequently, based on the resolution of the raster data, the representation of the entity model in terms of cell values can be done, wherein wherever there is a information, a specific and discrete value may be assigned, and wherever there is no information, a value of 0 may be assigned. So, the black polygon which has been shown in the entity model is information which is present, and thus the same can now be filled up in such a manner that it has discrete values. So, here in the next figure, the cell values corresponding to the filled polygon have now been assigned a value of 1, whereas the areas where there is no information, it is stored as 0. However, for GIS to understand this particular information, it requires some form of a file structure, so that it can understand the information that has been made present. So, in this particular figure C, the representation of the file structure has been made, wherein we find that there is a series of 0, 0, in all those places where there is no information, but wherever there is a information, it is represented as 1. It may be interesting to note that prior to this information, we have another line wherein certain informations have been given. So, what is this particular information? The first line in the raster file is basically a header that gives information regarding the cell size of the file and the maximum value that a cell may have. The first two values indicate that there are 10 rows and each rows has 10 pixels or columns, while the value 1 indicates the maximum value that a cell may have. Thus, in this example, the value of 0 represents cells having no entity value, while 1 indicates the presence of entity values. In raster data structure, different spatial features such as buildings, water bodies, contours, roads may be stored as separate data layers. That is, these features are stored in 4 separate data files, each representing a different layer of spatial data. However, if the entities do not occupy the same geographic location or cell in the raster model, then it is possible to store them all in a single layer with a entity code given to each cell. This code represents that which entity is present in a cell. An example of this case is shown in the next figure. Here what we find is that within a entity model, there are 4 types of information which do not overlap. For example, forest, water, residential, cultivation areas, these will not overlap amongst themselves and will have discrete and separate locations. So, now what we can do is, rather than creating 4 different files wherein pertaining to each information a small portion may be utilized to store the values and the rest may be kept blank, what we can do is provide separate entity codes to each of the information which is there. That is, for all cultivated areas assign a code 1, for forest assign a code 2, for water assign a code 3, for residential areas assign a code 4. So, based on these codes, now we find that the cell values have been correspondingly provided the entity code values and they are having very distinct locations. The file structure of this particular type of information can be now seen to be represented in a slightly different manner, specifically the header file. The header file now, as a matter of fact, has a small change in comparison to the previous one. The header file now reads 10, 10, 4, which means 4 is the maximum value which is there and 1 is the default start value. So, in this particular manner, the information has been stored in a file structure for a raster base database. Now, let us look at vector database structure, vector data structure. The entities like points, lines and areas can be defined by a coordinate system. One of the simplest vector data structure to represent a geographical image in the computer is a file containing x, y coordinates that represent the locations of individual point features or the points used to construct lines and areas. Here in this particular figure, a very simple vector data structure using point coordinates to describe a land parcel. Here it is a very simple land parcel shape has been considered, which is rectangular in shape. So, it has 4 corner points, each point has been designated by discrete x and y values. So, the first point corner has been designated as x 1, y 1, the second one as x 2, y 2, the third one as x 3, y 3 and the fourth one as x 3, x 4, y 4. Now, how this is would be converted? This is now going to be converted into a list of x and y values in a form of a file which we call it as a spaghetti file. So, all the points their x coordinates are listed in one column and y values are listed in the y column. Well, it is a very simple way of representing the information, but information in real world is not very simple. It is a complex scenario and thus this approach has certain limitations in dealing more complex spatial entities. For example, now what we can do is divide the land parcel into different segments. Say the land is now divided in such a manner that along the edge 3, 4 at the center there is a division. Similarly, the midpoints of the edge 1 and 6, this is divided at its midpoint and similarly 2 and 4 the midpoint is divided and these are joined by lines to form a configuration of 3 plots consisting of now polygons which are 1, 2, 3 and 4, which has been designated as plot 1. Then plot 2 is consisting of point 3, 4, 5 and 8, while plot 3 is consisting of points 8, 5, 6 and 7. If the simple data structure is used, here there will be duplication of data to define each entity individually, and the problem becomes serious when there are large number of entities. So, to address this problem, sharing of common coordinates of adjacent points is done by point referencing. Numbers are given sequentially, indicating that which point are associated with which point. So, what we call this as a point dictionary file. So, point 1, its coordinates values are stored in the point dictionary file. Similarly, the values of point 2, 3, 4 and 5 till 8, all these are provided. This is now supplemented by another file which describes the areal extent of each of the plot. So, this is what we call it as a polygon file, which will consist of two information. First is the identity and the second is the points which connect this particular polygon. So, under ID we will have plot 1, and this along with this we under the point column we will indicate points 1, 2, 3 and 7 to form this particular plot. Similarly, plot 2 would be represented by the points 3, 4, 5 and 8, and plot 3 would be represented by points 5, 6, 7 and 8. So, what we find now here is that some of the points which were common, they have now been taken care of without any repetition. The polygon file has now identified the extents of each of the plot entities, and thereby what has happened is a very simple data structure has now appeared or emerged. Well, we can complicate this problem further. What we can do is, instead of dividing it to 3 plots, this can now be divided into 5 areas, wherein there is a central area lying at inside, and this is divided into different blocks, wherein each of these could represent say 4 stalls in a say World Book Fair. So, there would be different regions indicating different stalls which have been occupied by different users, and in the center there is a information center. So, that people can go there, collect information regarding where the stalls are and proceed ahead. In a GIS representation, this may have to be carried out in such a manner that it consists of points, lines and polygons and the entities which are adjacent to it, so that a topological data structure that contains this information is now required. So, this may be represented in this particular manner, wherein all the points which are defining the different plot areas or stall areas, we have a node file, wherein each point has a ID and the x and y coordinates are indicated for along their side. Now, based on this, we now create another file which we call it as the segment file, and the purpose of this segment file is to provide a linkage between all the informations, wherein it tells that what is present on the left hand side and what is present on the right hand side, that is its topology is defined. So, now let us look at each of the stall areas that we have in such a manner that we now start to look at the lines which are forming the stall area. So, the first line is A, its start node is 1, end node is 2. When we look at the connectivity between the other objects, on the left hand side it has a polygon 101, on the right hand side there is nothing, that is this is outside the information space, and that the line is of a length 10 meters. Similarly, we can go and identify the side C, which provides for which the start and the end nodes are designated as 2 and 3 respectively. On the left hand side it has the polygon 102, and on the right hand side this is outside the feature space, again the length is 10 meters. So, in this manner the file segment will provide the information for each of the lines, thereby its start and end nodes would be identified, and its topology on the left and right will also be indicated along with the length. Well, when a line is inside, for example, the line O, its start and end nodes are 11 and 12. However, on the left hand side we have the polygon 105, and on its right hand side it has the polygon 103, and the length of this particular line is 7.07. So, in this manner all the lines have now been defined, so that its exact location and correlation amongst other lines and other objects are identified. So, what we do is, from this we create a polygon file, and this polygon file will now identify the typical regions occupied by each stall, and it will also identify the points which will form the area of this particular polygon. So, the polygon ID 101 consists of the segment list A, J, M, I and H. Similarly, polygon 2 consists of the segment list B, C, K, N and J and so on. So, in this manner the connectivity of the lines within the polygon have now been established. Now, the next information which is important, and that is its attribute. This attribute could be that what is the name of the polygon, what is the area of the polygon. These could be informations which may be required. So, it could be possible that the authorities who are organizing this fair, they may like to levy some charges as per the space occupied by each stall. So, the polygon attribute file will now have the name. It may have two variables. The first variable may be the name of the stall, the second variable may be the area of the under each stall which is there. So, polygon ID 101, its name attribute is Punjab stall and its area is 87.5 meter square. Similarly, polygon 102 is Rajasthan stall and it occupies again an area of 87.5 meters square. The polygon ID 103 is Maharashtra stall and it has a polygon area of 87.5. Similarly, polygon 104, its name is Kerala stall and it again occupies an area of 87.5 meter square, while the polygon 105 is West Bengal stall and it only has a area of 50 square meters. Now, with this information, other activities such as charging of hire of rents can be undertaken. There are numerous ways of providing topological structure. The example given in the overleaf illustrates the basic principles of topological data structure. Topological data structure represents connectivity between entities and not their physical shape. The table ahead represents the basic requirements of the entities of point, line and area to have a topology. So, let us look at the topological requirements of basic spatial entities. For a point entity, the requirement is a geographical reference to locate it with respect to other spatial entities. For line entity, it must be an ordered set of points known as an arc, chain or segment with a defined start and end points, which also gives the line direction. And the third entity could be area, which may have data about the points and the lines used in the construction of that area and how these are connected to define the boundary. So, let us look at the basic requirements of a topological data structure. First is no node or line segment should be duplicated. Line segments and nodes can be referenced to more than one polygon. All polygons should have unique identifiers, and island and whole polygons can be adequately represented. Having had a look at the manner in which some of the entities which relate in terms of point, lines and areas, now let us look at some of the entities which have fuzzy nature, and these can be represented by modeling surfaces. Surface entities such as elevation, population, pollution, rainfall are also required to be represented in GIS along with the entities such as buildings, roads, water bodies and forests. These surfaces vary in space, hence in order to show their variation, a convenient form is to represent them through trend or surface models such as digital terrain model. DTM is a set of digital data of x and y and z coordinates used to model topographic surfaces. More precisely, when DM represents height data as z coordinates, it is called the digital elevation model. Since it is not possible to have an infinite number of height values to model a surface accurately, the actual surface is approximated considering only a finite number of observations. In raster GIS, a DTM is represented by a grid in which each cell contains a single value of the height or the terrain covered by that cell. The accuracy of the terrain modeling by this approach depends on the spacing, that is the resolution of the grid and the complexity of the terrain surface. In a vector DTM, it is like a raster DTM with the difference that the vector DTM has regularly spaced set of spot heights, as one can see in the figure given below. In vector GIS, to represent the terrain surface with irregular height data, the common practice is to use tin, which creates a mosaic of irregular triangles by joining the points where spots heights are known by straight lines. The vertices of the triangles in a tin represent the features such as peaks, depressions and passes, and the sides represent ridges, valleys, whereas the surface of the individual triangle provides the area, gradient, that is the slope, and orientation, that is the aspect. Storing these values in tin as tin attributes helps in further analysis. The tin model has the following advantages. First is efficiency of data storage, and second is fewer points required to represent flatter areas. Having done this, now we have to model the connectivity between lines. So, let us look at modeling networks. A set of interconnected linear features such as a road, railway line, telephone lines through which goods and people are transported or along which communication of information is processed is said to be a network. Since network models in GIS are abstract representation, the use of vector data model and the raster data model is not suited for network analysis. The figure below shows a vector network model made up of some arcs, that is line segments, and node elements as any other vector data, but with the addition of certain special attributes. So, here the double arrow represents two-way flows, while single arrows represent one-way flows. The arrowheads show the end nodes and dots represent the vertices. So, let us look at the definition of attributes used in networks. Arc, it is providing the network link for informations such as roads, railways, power lines, cables and pipelines of utilities, rivers and streams. Node, it is the end point of network links. So, it may indicate or represent features such as stops, centers, junctions in transport networks, confluences in stream networks, switches and values in utility network. The next attribute is stop, that is locations may be visited, that is a bus stop, a pickup or delivery point in a delivery system. Then center, that is discrete locations in a network, for example, shopping centers, airports, hospitals, shops, schools, hospitals, cities at a smaller scale. Then turn, that is transition from network link to another network link at a network node. Turns across oncoming traffic on a road network take longer than turns down shiftways, whereas turns that go against the flow of traffic on one-way roads are prohibited altogether. Now, let us look at some of the specific type of network activities which is there. First is impedance. Impedance is the cost associated in traversing a network link, stopping, turning or visiting a center. It may be the time to travel from one node to another, or in the case of a delivery van, time, fuel used and the salary of the crew. Different links have different impedance values, as it depends on the factors such as traffic volume, traffic control systems and topography. Network has two key characteristics, that is impedance and supply and demand. The various forms of impedance values that may be linked to a network are shown in the table below. In this, the impedance values are shown and their corresponding symbols are also shown here. So, one way flow, two way flow, narrow street, wide street, junctions controlled by traffic light, junctions with no turn, van depot, storage warehouse, all these could be some of the typical symbols that could be used by the analyst to represent certain forms of impedance. Next characteristic is the supply and demand. Supply and demand is also an important aspect of network analysis. Supply is the quantity of a material available at a supply center to meet the demand associated with the links of a network. For example, the number of LPG cylinders required in a certain area is the demand, whereas the number of LPG cylinders available at its store is the supply. Correct topology and connectivity are extremely important for network analysis. With this, we have now discussed the various types of data structures which could be used, data models which could be used to represent the information in a GIS framework. In my next session, I would now like to focus on GIS database structure. Thank you.